5.4 discusses concavity, and we use the second derivative test to determine the concavity of the original function. Now let's read this together. I'm going to grab my highlighter. Okay, so the first derivative we say is dy over dx. This is the rate of change of f of x with respect to x. Okay, let's think of this. Yes, rate of change. We often say the word slope here. But let's think of terms of rate of change. So if dy over dx is very large, then y is changing a lot for every x. Okay, the change in this numerator is much bigger than the change in the denominator if this derivative is large. You can think of the other way too. If this derivative is very small, that must mean that the rate of change of y is very small compared to a very large change with respect to this change in x. Because if this denominator is very large, then this will evaluate to be something tiny. Similarly, if we find this first derivative is equal to 0, then when we consider rate of change, we think then that there is no change in y with respect to as x changes. So if this is 0, the numerator is 0, and regardless of what the change in x is, the slope would be 0 or the rate of change is 0. Interesting to think about, and I'd like you to consider that and work that through in your mind. Therefore, when we take the second derivative, this is the rate of change of the first derivative with respect to x. Okay, so concave up, we know concavity, we talk about a parabola opening up or opening down. That's what concave up means, it opens up. Concave down would be opening downward. We look at this side here of the concave having a negative slope. So this would be the first derivative. Where the first derivative is negative, we know that the function is decreasing. We know that right at the bottom spot, the horizontal line, there's going to be a 0 slope. And if our slope is positive, it's going up. Therefore, when the first derivative is getting larger, so we see the derivative being negative, we see the derivative being 0, and then we see the derivative being positive, right? This derivative is getting larger as you read this graph to the right. If the derivative is getting larger, this rate of change is getting larger, then we know that the second derivative will be positive. We know it will be concave up. Okay, so the second derivative will be positive, which means that this original function was concave up. Similarly, when we look at the opposite here, if we start on the left here, we've got a positive slope. That would be the first derivative. We have a first derivative equal to 0, or the slope is 0 here, and then the first derivative turns negative to go downward on this curve. Here, the first derivative is getting smaller, going from positive to 0 to negative. Then we know that the second derivative will be negative. And the second derivative being negative implies the original function will be concave down. Now, we also talk about inflection points. So on the first derivative, we talk about the point where the increasing changes to decreasing or decreasing changes to increasing. We call that the critical point. When we're taking a second derivative, so read on the bottom here, wherever the second derivative of x is equal to 0, then the derivative of the first derivative must not be changing. It's a constant. This point is called an inflection point. We're going to draw them on where the derivative is constant. Sorry, didn't mean to have that there. Derivative is constant when the rise will equal the run. So this, does that look 45? I think it is supposed to be right there. And similarly about here. And on the previous graph, the rise equaling the run. So we're going to have an exact slope of 45 degrees, right? So maybe this isn't quite drawn in right, but these would be the inflection points where the first derivative is a constant term. So for the following questions, we want to determine the intervals where the function is concave up and concave down. We need to know where the second derivative is positive, that would be concave up, where it's 0, and where it's negative, concave down. How do we determine where functions are positive and negative? Dun, dun, dun. We use sign analysis, which I know you all love. At least I do. Okay, so for this first question, I would like you to, number 1, find the first derivative. Number 2, find the second derivative. Set up a sign analysis then of the factors of the second derivative and find where this original function is concave up, the positive part, and concave down, the negative. So here we find that this function is concave down over this open interval. The inflection point is the place where the graph changes from being curved downward to being curved upward. That's the inflection point. And the inflection point for the first derivative would be the spot where that derivative is constant. Okay, and concave up then over this interval. Now let's look at the graph here. I'm hoping that we can just see it. Yeah, there we go. Okay, so here it's the original function in red. You can see that. The first derivative is in blue. So again, now remember the first derivative shows increasing and decreasing. So we see that in the original function red is increasing to this point, and that would be shown by the first derivative's graph being positive above the x-axis. And then the function starts decreasing here, and that's shown by the first derivative being negative. Okay, and then the second derivative is in green. You can see that there. Now the second derivative shows concavity. So look at the first original function. We see here it's concave down until right here, this inflection point where it starts changing to concave up. And you can see that then this whole spot that is originally concave down is negative on this second derivative. Then right here at this inflection point, the graph is concave up, and you can see that's shown by the second derivative being positive there. Very, very intriguing. Okay, let's move to number 2. Okay, go through those same steps, okay? First derivative, second derivative, sign analysis of the factors of the second derivative, and then determine that intervals where they're concave up and concave down. Pause it, please. So after that work, we can see that it's concave down here and concave up there, and we see that there's an inflection point. Now, you can see here that there was also what looked like an inflection point here, except the sign analysis has shown that this graph will be concave down this whole way, so we don't include that. So the intervals here would be negative infinity all the way to 1, and here would be 1 all the way to positive infinity. Now remember, these intervals are open, round brackets, because it doesn't include this inflection point, and we know that always when we go to infinity, we use a round bracket. Here's the graph for this one. Purple is the original function, and red is the second derivative. So you can see here on the purple function, right on this spot, we've got it concave down until about, well, a little bit, I went a little too far, concave down there. So that tells us that our our second derivative, which is red here, should be negative, 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 and it is negative, negative. You can see this tangent to and not crossing point there, and stays negative until exactly at the change, the inflection point, which we found to be 1. Yes, right here on the original graph. I'd like you to pause it and analyze this graph for C. We're going to skip over D and go to E. E is a longer question. You can see that it uses the quotient rule to find the derivative, and then the second derivative as well, so that takes a little more room on your paper. I'd like you to go through those same steps, and I'll put my work on here, and then you can compare it at the end. Well, that was a long one. But you can see the answer there in the exact same steps. Let's look at the graph to just confirm that. So we can see here the blue is the original function, and you can see it's a rational function, so it does follow that pattern, the blue. It's got asymptotes at 1 and -1, which makes sense. Second derivative here is the black, and you can see that where the blue lines are increasing, the black lines are positive, and vice versa. Third line, which we're looking at now, the second derivative, is green, and you can see where the original function is concave down, that the green lines will be negative, and same vice versa. Okay, we're going to stop here, and you can do a couple questions from your textbook involving this, finding the intervals where the function is concave up or down using the second derivative.